Muscle fibers consume fuel for explosive contractions, while joint cartilage absorbs the heavy mechanical impact of every step. These macroscopic functions are distinct, yet both the energy mobilization in the muscle and the shock absorption in the joint rely on the same class of molecular building blocks. We define carbohydrates as aldehyde or ketone derivatives of polyhydric alcohols, or as the specific compounds that produce those derivatives upon hydrolysis. This atomic model illustrates the basic empirical formula, CnH2ON. It is a carbon backbone hydrated by water molecules. To understand how this ratio builds biological matrices, we must track the architecture from its smallest monomer units up to complex heteropolysaccharides. Throughout this process, we will see how the physiological utility of a carbohydrate is dictated by microscopic variations in its stereochemistry and structural isomerism. Monosaccharides are classified by their primary functional groups. If they contain an aldehyde, they are aldoses. If they contain a ketone, they are ketoses. Hexoses, 6-carbon sugars, provide a clear comparison. Glucose is an aldohexose. Its aldehyde group is located at the top, attached to the first carbon. Fructose is a ketohexose. Its ketone group is lower on the chain, at the second carbon. Beyond the functional group, we determine absolute configuration using D and L isomerism, which is based on the orientation of the penultimate carbon. The penultimate carbon is adjacent to the bottom primary alcohol carbon. In a hexose, this is the 5th carbon. Notice its hydroxyl group. If it sits on the right, it is a D isomer. If on the left, an L isomer. While the functional group sets the chemical class, a single hydroxyl group's spatial orientation determines the specific molecular isomer and its interaction with biological systems. This spatial sensitivity is seen clearly in epimers. This isomerism occurs around only one specific carbon atom in the chain. We track this by comparing D-glucose to its primary physiological epimers, D-mannose and D-galactose. Glucose and mannose are C2 epimers, differing only by an inverted hydroxyl group at the second carbon. Glucose and galactose are C4 epimers, varying entirely at the 4th carbon. If we compare galactose directly to mannose, however, the relationship changes. Differing at both the 2nd and 4th carbon positions, galactose and mannose are optical isomers, but they do not meet the definition of epimers. This single hydroxyl flip at carbon 4 is the only structural difference between glucose and galactose. Because the body requires distinct enzymatic pathways to recognize and process each one, this minor chemical shift determines the molecule's physiological destiny. In a biological environment, linear models represent less than 1% of a sugar's existence. In solution, the molecules bend into 3-dimensional geometric rings. A 6-membered ring containing 1 oxygen atom is a pyranose. A 5-membered ring is a furanose. As glucose cyclizes into a pyranose, the former carbonyl carbon, carbon 1, becomes a new stereocenter. This is the anomeric carbon. Its orientation determines the final configuration of the cyclic sugar. If the hydroxyl group on this carbon points down, it is the alpha anomer. If it points up, it is the beta anomer. These forms are not static. In solution, they interconvert through a process called mutarotation until they reach a dynamic equilibrium. This interconversion ensures they maintain the 3-dimensional geometry required to build the body's complex biological polymers. Monosaccharides connect through condensation reactions. As a hydroxyl group and hydrogen detach as water, an oxygen bridge forms between rings. This is a glycosidic bond. If carbon 1 bonds to carbon 4 of the second glucose, we name it a 1,4 glycosidic bond. Polymers made of entirely identical monosaccharide units are called homopolysaccharides or homoglycans. Glycogen is a primary homoglycan. It is a highly branched polymer composed of repeating alpha-D glucose units. This structure allows the body to store vast amounts of glucose in the liver and muscles, creating a critical energy reservoir. By utilizing these simple, repeating linkages, homoglycans provide a dense and easily mobilized source of fuel for cellular work. Unlike homoglycans, heteropolysaccharides are polymers of different varieties of monosaccharides or their derivatives. Glycosaminoglycans, or GAGs, are a vital class of heteropolysaccharides, consisting of long, repeating disaccharide units of carbohydrates and proteins. GAGs possess specific physical properties. They are highly viscous, slippery, and carry a strong negative charge that makes them hydrophobic. These properties are essential for joint health. Hyaluronic acid, for example, serves as a lubricant and shock absorbent that allows skeletal joints to bear weight. Other GAGs perform diverse roles, such as chondroitin sulfate, maintaining tissue structure, and heparin acting as a biological anticoagulant. When the body fails to maintain these specific molecular geometries or metabolic pathways, the result is clinical pathology, ranging from the insulin dysregulation of diabetes mellitus to the enzymatic failures of galactosemia. From a single heartbeat to a sprinting stride, the structural diversity of human biology is built upon the precise, microscopic laws of carbohydrate stereochemistry.